Okay, YouTube, in this last video, we're going to look at a couple of application examples of solving quadratic equations. But before we do that, one thing I want to mention is that I've included this little, suppose you just call it a table here. And in this table, what you'll see is the description in form of, say, a quadratic equation and then the most efficient solution method to solve such an equation. So what I can tell you is, if at all possible, we like to solve quadratic equations by either factoring or using square roots, but it's not always a possibility. And so sometimes we have to complete the square or use the quadratic formula. So let's go ahead and run through these very quickly, and then we'll talk about these application problems. So in terms of ax squared plus bx plus c equal to 0, if it can be factored, then basically what I'm going to tell you is factor it and use the zero product principle every day of the week. It's always going to be the quickest way to solve a quadratic equation. Now, when you look at this form right underneath it, it says ax squared plus bx equals 0. You notice that the c term is lacking here. It has no constant term. But this right here, I noticed that these both have an x in common, and so this is really, really factorable as well. So whether your c term is 0 or not 0, the first thing you always look for is to factor it. That's why I've kind of listed it twice, because it's the easiest way. Now, if we have something of the form ax squared plus 0x plus c equals 0, or that is, you're lacking an x to the first term and you just have an expression in x squared, then really, if that's the truth, then what we're going to do is we're always going to solve for the squared quantity and then just apply the square root property, which means we'll just take the square root of both sides. So as far as what we would do in terms of these last two cases, again, if we have an expression in x squared and it's equal to some number d, we'll use the square root property. And last but not least, we say that if it's ax squared plus bx plus c equals 0 and it can't be factored, or at least the factoring is just too difficult to perform, then we'll just use the quadratic formula. So you'll notice that nowhere did I say solve it by completing the square, even though it's an important method, we want to know how to use it. Basically, we're either going to factor it, use square roots, and if we can't do either of those things, we'll write it in standard form, set equal to 0, and then apply the quadratic formula here. So let's take a look at this last couple of examples. This first one here, it says the formula P equals 1/100th of a squared plus 5/100ths of a plus 107. This models a woman's normal systolic blood pressure, P. So P is our blood pressure here at age A. So this A here represents the age that they're at, and it would tell us the normal systolic blood pressure. And of course, this is just a model, so it's approximating it. But what we want to do is say, use this formula to find the age to the nearest year of a woman whose normal systolic blood pressure is 115 millimeters of mercury. So I don't have this graph that's also included here with this example, but what I can say is this. What we've been given is this. We've been given the blood pressure, P, and we've been asked to solve backwards for A. And so what we'll do instantly is this. We'll say, well, if P is equal to 115, let's rewrite this equation where we substitute 115 in for P on the left side, and then we get this. We get 0.01 a squared plus 0.05 a, and this was plus 107. So the idea here is that we want to go solve this equation, and we've got some really atypical values. I mean, these are not fun to deal with. So when I look at this, the first thing we want to do before we solve it is essentially get it equal to 0. So I'm going to move this negative 115 back over to here, or at least it becomes a negative 115 when I displace it to the other side. So using the reflexive property, I'm actually going to rewrite this as 0.01 a squared plus 0.05 a, now minus 8, which really is the result you would get if you took 107 minus this 115 here, you get negative 8. So this is all now equal to 0. And now that it's equal to 0, we could start by saying, well, we could solve this by factoring it if it factors. I notice that I can't use square roots because I have an a to the first as well as an a squared. Or we could use the quadratic formula. Now, as far as using the quadratic formula goes, we said, well, use this if it's too difficult to factor. I have no idea what this factors into. So I'm really inclined to say, well, then here's what we'll do. We'll just go ahead and list out the values of a, b, and c now that we have this in general form. That is, standard form set equal to 0. So having these listed now, we could say really the solution for a, in this case we have a and not x, is we have negative 0.05, which is our b value here, plus or minus the square root of, now this will be 0.05 squared, minus 4 times a, which is our 0.01, times c, which is our negative 8. And this is all over 2 times our a value, which again is this 0.01. So we get a. And you know what, I'm going to get a decimal here, so let me write approximately here in a moment. What we'll do for right now is this. I'll get my calculator rocking, and actually I'll pull out my paper tape here so we can see our calculations as we go. The best place to start really is inside the radicand. So I'm going to take that 0.05 and I'm going to square it. And so we get this here. So we say, you know, power of 0.05 to the second is this value right here. Now we're going to subtract from our answer this, in parentheses, we'll say 4 times 0.01 times 8, which is negative, and end parenthesis there. So we'd say that comes out to equal this right here. So that 0.0025, you know, minus that value right there, we get this decimal. So what is in here is exactly equal to that. And maybe I write this down and say negative 0.05 plus or minus, just to show you here that we're not dealing with anything too unordinary. We just need to take our time. But, you know, pulling out the calculator again, we said 0.3225. So 0.3225. So now what we're going to do is we're going to take the square root of our last answer. So I'll go ahead and do that. Square root equals this. Okay. Whoops. Let me try this again. 0.3225. Let's take the square root. I'm not worried about the paper tape over here any longer. So the square root of that is approximately this. So now what I'll do is I'll add this to the memory of my calculator, because what I want to do is I want to take negative 0.05 plus this value and divide it by 2 times 0.01, which, by the way, this bottom part right here is really 0.02. So we'll do this. We say I've added it to my memory plus, and then we'll do this. We say 0.05 negative plus memory recall, which was all of this right here, actually. Let's try this again. We have 0.3225 square root. Clear the memory here. So we'll memory plus this. So now I have negative 0.05 plus my memory recall. This looks familiar. We say equals. And then we'll divide that by 0.02. And so I get 23.39, and that is approximately 23.39. And I'm going to write years. Now, here's the thing. I should go back and check this for negative 0.05 minus this over 0.02. But one thing I want to comment on is that you actually get a negative value, which in this instance, it really doesn't make a whole lot of sense that a woman would be negative years old if her systolic blood pressure is 115 millimeters of mercury. So we're actually able to determine that that's probably the normal range here, at least for systolic, for about a 23-year-old if we're going to do this to the nearest year, to about 23 years old. Okay. So now, let's take a look at our last example here in this video, in which we're going to use the properties of the Pythagorean theorem. But it says a 25-inch television set. They say that the length of the screen's diagonal is 25 inches. I mean, I guess this is an embarrassing thing to admit. I never really realized this when I was growing up. But then I got older, you know, and I learned that 25 inches, I'm like, what is that measuring? It's actually measuring this part of the television. It's measuring the diagonal of your screen. So if you knew that, well, good for you. You knew it before I did. But we say if the screen's height is 15 inches, we're saying that this is 15 inches right here, then what is the width of the screen? I'm just going to use X to represent the width. So the nice thing about this screen is, at least I hope it's constructed this way, is that it makes a right angle in its bottom right corner here. You could look at the same triangle on the top left here. But essentially what we want to do is we want to solve for X in this equation. So recall that for a right triangle, this must be a right triangle here, where the legs are A, B, and the hypotenuse is C, we have the relationship that the sum of the squares of the legs is equal to the square of the hypotenuse. So using that very same relationship here, we could say, well, then the sum of the squares of the legs, which is x squared plus 15 squared, has to come out to be the same thing as 25 squared. So to solve this, here's what we'll do. We'll just go ahead and simplify a little bit. We get 15 squared is 225. 25 squared is 625. And then I look at this and I say, well, look, this is some quadratic equation. It's not quite set equal to 0 yet, which would be the first thing that we typically do. As a matter of fact, if I subtract 625 from the side, which is an unnecessary thing, but I want to show you this, I would get x squared minus 400 is equal to 0. And so if I said, well, how would I solve this? I mean, looking back at this table over here, I noticed that we're completely lacking in x to the first term, which means that we can just use square roots, solve for the squared term, and use square roots. So what I'll do is I'll add that 400 back to the right side, and I get x squared equals 400, and then we'll just take the square root of both sides. So the nice thing about the square root of 400 is it's actually a perfect square, and we get positive and negative square root of 20. So in the context of this problem, I want to consider this. We get two solutions here, positive and negative 20, but basically the only one that makes reasonable sense in this this situation, this particular situation, is that this is a positive 20 in this dimension here.